everyone, and welcome to our presentation on Selective Repeat Protocol for Computer Networks. The presenters in this video are me, Darlene, Drew Cavanaugh, and Cameron Nixon. I'll be highlighting what Selective Repeat does and its properties. Drew will go over an example problem, and Cameron will take over the pros and cons of Selective Repeat. First, let's understand the properties and mechanics of Selective Repeat, or in other words, SR. Here are some basics to help us grasp what SR does. So Selective-Repeat is a pipeline sliding window protocol in the transport layer which sends up to n UNAC packets in a pipeline. For each packet, the receiver sends an individual ACK or acknowledgement to the sender to indicate a successful receive. Some other protocols that are also considered a sliding window pipeline protocol is go back N, which we will talk about in later slides. Continuing on with the basics, we'll be discussing the window size of the sender and receiver. First rule off the bat is that the window size must be less than or equal to half the size of the sequence number space. So for example, if we're given a sequence of 6, the window size of the receiver and sender would have to be 3 or less than 3 because 3 is half of the sequence size of 6. But what does the sender and receiver do with this sequence and this size? Well, the sender moves the window size after each acknowledged packet. In turn, the receiver moves the window size for each received packet, meaning that it moves when end packets are reached and the sender has acknowledgement for those packets. Here you'll see on the left we have the sender size with the window size of 2. And on the right as well, we see also a window size of 2. You'll also see that the receiver window moves only if the sender receives acknowledgement of the previous packet. So when the packet is lost, the receiver window does not move. Next, let's go over some sender basics. Each UNAC packet has a timer that waits for an acknowledgement from the receiver. The sender only sends packets that have not gotten an acknowledgement for, and the sender window size is limited by sequence numbers that have not yet received an acknowledgement. So basically, the sender is dependent on the receiver. What does SR do with the timeouts? Well, every UNAC'd packet has a timer on the sender side that tracks the acknowledgement of that packet. If the timer expires, as in the receiver did not send an acknowledgement back, the sender will retransmit the UNAC'd packet. Here you can see that frame 3 gets lost in transit, so the receiver side does not send an acknowledgement back. Since the sender did not get the acknowledgement of frame 3 from the receiver, it times out and resends frame 3, even though frame 4 was already sent. So another question arises, so what happens to frame 4? Well, it turns out the receiver does not like things out of order, so it buffers and moves only when the in-order packet is received. The receiver wants the packets in order so that it can send it to the upper layer. So, in order is good, and out of order is bad. Now I'll hand it over to Drew, who will work through our example problem using Selective Repeat protocol.
Let's look at a really simple example of selective repeat. Here we see frames for both the sender and receiver with a window size of 4. This example is a freeze frame where the packet with sequence number 1 was just acknowledged by the sender. The sender's window shifts and the first packet, called S sub f of the window, has sequence number 2. The next packet to be sent, called S sub n, has sequence number 5. Packets with sequence numbers 2, 3, and 4 have already been sent by the sender, and they are awaiting acknowledgement. On the receiver side, packet with sequence number 2 has already been received and has transmitted the acknowledgement packet back to the sender. The receiver window shifts forward, with the next expected packet, called R sub n, having sequence number of 3. Since the window size is 4 in this selective repeat example, the receiver is actually expecting any packet within that window size. This means that in this snapshot, any packet with sequence numbers 3, 4, 5, or 6 can be received without any error or retransmission. Since the receiver has not yet acknowledged the receipt of packets with sequence numbers 3 and 4, that means they are still in transit from the sender, as shown. Once the sender has received acknowledgement from packet 2, the window shifts forward to continue transmitting the frame. The packet with sequence number 6 will immediately be sent now that the frame has shifted. Now let's look at a frame-by-frame example scenario using selective repeat where packets are lost in transmission. We will use the same setup as before. The window size is still 4. The sender starts by sending all of the frames in its window. The sender marks all 4 sequence numbers as expecting acknowledgement from the receiver. The receiver is also expecting these incoming packets. In this example, all 4 packets were received by the sender. The receiver window moves forward 4 spaces since all 4 packets were received uncorrupted. Packets with sequence numbers 0 through 3 are marked as received, and the receiver is free to acknowledge the receipt of those packets in the future. However, in the following iteration, the packet with acknowledgement number 1 is lost in transit. The other acknowledgement packets are not lost, however. When the sender receives acknowledgement of packet 0, the frame shifts forward 1 spot, awaiting the acknowledgement of the next packet it is expecting. S sub n shifts to packet 4, and the sender immediately prepares to send it. Now, packet 2 has been acknowledged, and packet number 4 has been sent. However, packet number 1 has still not been acknowledged since the acknowledgement received was lost in transit. Because of this, the sender's window does not yet shift. It is still expecting to receive the acknowledgement packet. Selective repeat assumes that the packets were placed out of order in transit, so there is no need to resend the packet just quite yet. Moving onward, packet with acknowledgement number 3 was just received by the sender and marked successfully acknowledged. Also, the packet with sequence number 4 was received by the receiver, and that receiver's window will shift forward 1 frame. However, the sender is still waiting all acknowledgement for packet 1. The timeout for frame 1 will expire soon. Now here's where it gets interesting. The internal timeout clock for S sub f has expired, so the sender has determined that the packet was lost in transit, either on its way to the receiver or back to acknowledge the sender. Either way, the packet must be retransmitted to ensure proper receipt. The sender retransmits packet with sequence number 1. Meanwhile, the acknowledgement packet from the receiver for packet 4 is on its way back to the sender. Both packets in transit are received successfully. The receiver sees that the packet with sequence number 1 was already received, so there is nothing it needs to do on its side. It will begin transmitting the acknowledgement of packet 1 again. On the other side, the sender understands now that the packet with sequence number 4 has been acknowledged by the receiver, so there is nothing left to do in this window except await the acknowledgement of packet number 1. In this example, communication between the sender and receiver becomes bottlenecked by waiting on a straggling packet to confirm to the sender that the data was successfully delivered uncorrupted. The window for the sender will not be allowed to advance until it knows for certain that the packet or packets holding it up have been acknowledged by the receiver. Upon receipt of acknowledgement packet 1, the sender can finally move on. The window moves forward 4 frames to where S sub f and S sub n are now at sequence number 5. The sender and receiver are now fully synchronized, and the sender will continue sending packets, rest assured that the receiver has received the data correctly throughout this time and moment.
Hi, this is Cameron Nixon. I am here to discuss the pros of selective repeat and the cons of selective repeat, and when and why you should use them. Okay, to start off, selective repeat only retransmits the packets that were explicitly lost versus how go back in retransmits all the packets that it suspected were lost. This ultimately causes less bandwidth to be used with selective repeat if a lot of errors were made during the transition, and this is a big pro for selective repeat. As you can see down here with selective repeat, there was only one damaged packet, and it ultimately discarded it and then resent it. Versus how over here and go back in, you can see how ultimately we end up getting one damaged packet, but we discarded 3 and had to resend 3 packets versus only the 1. However, this comes with one major con though. This is much more time consuming and expensive to implement. So, well, let's break it down and see. Selective repeat's window size, as you can see, is much more complicated of a formula rather than go back in's relatively simple just n-1. This is a big difference between the two, and ultimately there's a couple of reasons for this complexity. We're going to take a look at those now. Okay, in selective repeat, the sender is only able to search the currently requested frame. No other frame has the ability to be accessed at all. Versus how you can go back in, no searching is required at all, and you can just get any frame you want. Another big reason for this is the receiver constantly has to keep sorting the packets in order to maintain the sequence of the frames. Otherwise, selective repeat will just fail. Go back in doesn't have to do this. When you move back in selective repeat, that order has to be maintained because it has to retransmit. I don't really retransmit them, but keep them in a buffer, like how it says down here. Lastly, the receiver has to store the frames received after the damaged one in a buffer until the damaged one is replaced. Again, go back in doesn't have to deal with this. This goes back to the second reason. Since they're in the buffer, you got to maintain that order. Otherwise, you're going to end up with a mess. So, what? Why is this a big issue? Well, this leads to 2 major factors in development. You have increased time and increased complexity. And sometimes, when you're developing something, you don't want that. Sometimes they say time is money, and you don't want to be wasting a lot of time fiddling around when you need to be getting stuff done. It's about managing your time. Think of it like this. Think of the packet as this tree. You have 2 problems. You have a tree and a stick. Both represent 2 problems with packets. You have 2 different sets. Imagine go back in as this simple but easy wood chopping axe. And imagine selective repeat as this nice modern chainsaw. Now, if you're going to go cutting down a tree, which one are you going to choose? Would you choose the chainsaw or the axe? Knowing me, I choose the chainsaw, as ultimately it's more efficient. Although it is more complex, and yes, it can break down, it requires a fuel source or a power source like gasoline or electricity, and there's much more complex and moving parts. It takes more upkeep to maintain, and generally it takes more time to set up, but you get returns and dividends because it cuts down the tree much faster than if you're going to be sitting there wailing on it all day with a simple axe. Now imagine you need to cut this simple stick. This stick, I don't know about you, but it seems a bit overkill to whip out a chainsaw when I can just take an axe and get one good swing in and instantly cleave the thing in 2. By the time I'm finished getting the chainsaw fueled up or plugged in, getting it ready and all that stuff, to where I can finally crank it up, the person with the axe would have already chopped the stick in 2. I just wasted time. Ultimately, the choice to use selective repeat over go back in comes down to your needs as a programmer. If you are dealing with a large amount of packets with a reasonably high chance of errors, selective repeat is the better option. However, if you're just dealing with a small amount of data being traded back and forth, it might just be easier to implement go back in. You don't need all that complexity. You can just simply implement the easier and faster solution and ultimately waste less time.